So here's our third example for torque, and this problem is a classic problem. Here we'll be using both equations that we know for torque. So the definition of torque, or RF sine theta, and we will also use the Newton's second law equation for torque, which of course Newton's second law is force equals mass times acceleration, and so the rotational analog of that equation is torque is equal to our rotational inertia I times angular acceleration. So we'll use both of those equations in this problem. So we have this figure shows a uniform disk with big M of 2.5 kilograms and radius R is equal to 20 centimeters mounted on a fixed horizontal axle. A block with mass M equal to 1.2 kilograms hangs from a massless cord that is wrapped around the rim of the disk. Find the acceleration of the falling block, the angular acceleration of the disk, and the tension in the cord. The cord does not slip and there is no friction at the axle. So the main idea here is that because that disk, that pulley, has mass and radius and everything, it has a rotational inertia. So because of that, it's going to slow the fall of the block. If the pulley was massless and frictionless, like we have been using in the past before we learned about rotational inertia, that block would just fall right down at an acceleration of 9.8 meters per second squared. However, because the pulley has a mass m, we know that it's going to slow that block down. So let's look at the pulley first. I'm going to draw a little picture of the pulley. So we have our pulley here, we have our R, and then our tension pulling down on that pulley. So we can see that the tension in the cord, because it's the same cord, whatever tension we have for block M, when we draw that free body diagram, it's going to be the same tension that's pulling on that pulley, causing it to rotate. So the tension is the force. Now, the first equation for torque, of course, is equal to our RF sine theta. Now, in this case, R, that little r in the equation, is our radius, big R. So we get torque is equal to R times our force, which is the tension pulling on that radius, and then sine of theta here, this angle between R and tension is just 90 degrees. So sine of 90 is just 1. So what we end up getting here for our first equation for torque is R times tension, or radius times tension. Now the second equation that we have for torque, of course, is I times alpha. Remember, this is our rotational analog of Newton's second law, F equals ma. Of course, torque is the rotational analog for force, and rotational inertia is the rotational analog for mass. And then angular acceleration, of course, is the rotational analog for regular acceleration, linear acceleration, I should say. So we have these two equations. Since they're both equal to torque, I can set them equal to one another. So I end up getting RT is equal to I alpha. Now, the other thing here is that I know that we want to find the acceleration of the block, or linear acceleration. We want to find angular acceleration, alpha, of the disk, and the tension in the cord. So in this case, I have two unknowns here. Well, really, I have three unknowns here. I don't know the tension. I don't know the rotational inertia yet, but I do know equations for the rotational inertia. And I don't know this angular acceleration, alpha. So what I'm going to do here is first and foremost, I'm going to plug in the rotational inertia for the disk. So I know that since this is a disk, the rotational inertia for a disk is 1/2 mr squared. So that is going to be plugged into our rotational inertia here. So I get R times T is equal to 1/2 mr squared times alpha. And then the other thing I'm going to do here is I'm going to relate linear acceleration and angular acceleration. Now, the reason for this is I have this equation, and then I know that I can also draw an equation right an equation and draw a free body diagram for the block as it falls down, but that is a linear acceleration. So in order to relate those two equations, I'm going to have to convert this angular acceleration alpha into linear acceleration. So I know that linear acceleration, and that's the tangential acceleration, of course, is our angular acceleration times our radius. Here, angular acceleration then is equal to linear acceleration divided by radius. So then I'm going to take this whole thing, plug it in for alpha here. So we get radius times tension is equal to 1/2 mass times radius squared times the quantity acceleration divided by radius. So here, one of these radii are going to cancel. And then I see that on either side, I also have radius. So that radius cancels with the other radius. So what we end up getting here for our pulley is that tension is equal to 1/2 ma, where m is the big mass of the pulley, a is a linear acceleration or the tangential acceleration on the pulley, and t is the tension. So here I still have two unknowns. I know the mass of the pulley, big M, but I don't know the tension and I don't know the linear acceleration. So now I need to look at the block. I'm going to draw a free body diagram of the block and then use Newton's second law to write an equation. So my block here, I have tension pulling up, and then of course the force of gravity of the block pulling down. I know that this block is accelerating downward, so I'm going to call that a positive acceleration here. Also, a little note on signs here. We know that we call counterclockwise positive and clockwise negative on our rotations, but just like we usually call up positive and down negative, we can switch that orientation as long as we keep our signs consistent. So what I'm going to do here is I'm actually going to call that rotation, which is clockwise, I'm going to call that positive, and I'm going to call down positive. So here I'm just keeping these things consistent here. You could call down negative and the rotation direction negative just to keep that sign consistent. But again, it doesn't really matter here as long as you keep stuff consistent. So what I get here for Newton's second law is force of gravity minus tension is equal to mass times acceleration. Notice how I write little mass because this is the mass of the block. Force of gravity, of course, is little m times g, mass of the block times acceleration of gravity. Minus tension is equal to mass times linear acceleration. I'm going to solve this equation for tension because, again, I have two unknowns here. I have the tension and the linear acceleration. So solving this equation for tension, I get tension is equal to little m times g minus little m times a. And then now I have two equations for tension. I have this one right here and this one right here. And I have two unknowns here as well. I have tension and I have linear acceleration, both as unknowns. So what I'm going to do here is I am now going to set these equations equal to each other. So we get, let's do this in a different color. This 1/2 mass times linear acceleration. I'm going to bring that down here. And that's big M because it's the mass of the pulley, equals, and then let's do this in purple, why not? I get mg minus ma. Okay, setting those things equal to each other. I am then going to solve for our linear acceleration a because now that's our only unknown that we have. So solving for linear acceleration here, I'm going to add little m times linear acceleration to both sides to get it all on one side. So we get 1/2 ma minus little ma equals mg. I'm going to factor out a linear acceleration. So a times the quantity 1/2 big M minus little m equal to mg, and then divide both sides by that 1/2. I'm sorry, that should be a plus, right? I add that to both sides. Hopefully you caught that. And then I'm going to divide both sides by 1/2 times big M plus little m. So acceleration ends up being little mg divided by 1/2 big M plus little m. And so solving for linear acceleration, I end up getting the little mass, so the mass of the block, which was 1.2 kilograms, times 9.8, our acceleration of gravity, divided by 1/2 times big M, which was the mass of the pulley, which was 2.5 kilograms, plus little m, which was 1.2 kilograms. So we end up getting 4.8 meters per second squared. So that's our answer for the linear acceleration of the block as it falls down. And this makes sense, right? Because we know that since that pulley has mass, it's going to slow the fall of the block. So this should not be more or equal to 9.8 meters per second squared. It should be less than 9.8 meters per second squared, which it is. So now that we have linear acceleration, we can now solve for tension and we can solve for angular acceleration. Angular acceleration, of course, is just going to be this linear acceleration divided by radius. So that makes it a little bit easy to just plug in numbers. We get 4.8 meters per second squared divided by the radius, which was 20 centimeters right here. So that 20 centimeters, of course, we want that in meters. So that is going to be 0.2 meters there for our radius. So we get 4.8 divided by 0.2. The angular acceleration ends up being 24 radians per second squared. All right, and then last but not least, we are going to solve for tension. You can use either one of these tension equations, so the 1/2 big M times linear acceleration or the little m times our acceleration of gravity minus little m times linear acceleration. I'm just going to use the 1/2 times big M, the mass of the pulley, times acceleration, just because it's shorter. So we get tension equals 1/2 big M times A. Tension equals 1/2 times big M, which was our, what was that, 2.5 kilograms times linear acceleration, 4.8 meters per second squared. And so we end up getting here 0.5 times 2.5 times 4.8 is 6 newtons for tension. All right, so whenever you have a problem like this, you're going to kind of draw a free body diagram for the pulley, which I kind of did. And remember, it's the tension, that's the force that's causing the torque on the pulley. And then you have two different equations for torque. So you set them equal to each other. We set our RF sine theta equal to rotational inertia times alpha, which is angular acceleration. And we used that. We plugged in an equation for both angular acceleration, so this equation right here for our alpha. We also plugged in the rotational inertia equation for the disk because that's what a pulley is. And then we were able to cancel out a lot, like all of the radii, right? The r's that showed up, and we got a more simple equation. And then we used Newton's second law and our free body diagram of the block in order to get another equation for tension, and then we set those equal to each other and solved for all of our unknown variables that we wanted to solve for. So any problem like this, when you have a pulley and a block and they're attached by a tension cord like that, you're going to use the same approach. And this is a very common problem in physics. So remember all those kind of tricks that I showed you how to do on this problem, and hopefully the next time you see it, you will ace it.